Mr.Drover's cat, meaning my cat, lets out a nasty fart. Okay, a big toot. You probably heard of people using the term velocity when they describe how fast a car is going. Most of the time, they are actually referring to the speed. As you learned in the last video, speed describes the rate of motion of an object, but velocity describes both the rate of motion and the direction. Sometimes I use them interchangeably by accident. All people do, but remember there is a difference. You can determine the average speed of the car by looking at its speedometer. To determine the average velocity, you actually need both a speedometer and a compass to show you its direction. The difference between speed and velocity is the speed is a scalar quantity. A velocity is a vector quantity. All quantities in science can be classified as either a scalar or vector quantity. A scalar quantity is one that only indicates how much or the magnitude. A vector quantity does two things. It indicates how much, so the magnitude, and the direction of the quantity. A vector quantity is written with a vector arrow above the symbol. For example, the symbol for speed is V, and the symbol for velocity is a V with a little arrow on top. Let's talk about distance traveled and displacement, and how they are different. Distance traveled and displacement are two other examples of scalar and vector quantities that are related. Distance traveled is a scalar quantity, meaning it is a measurement of an object's change in position based on a starting reference point. Like, let's say use this guy for an example. Mr.Drover's cat, meaning my cat, lets out a nasty fart. Okay, a big toot. And me, Mr. Drover, moves 10 meters away from the cat. The cat in this case is the reference point. So what you would do is you would record the distance that I moved as delta d equals 10 meters. This indicates that the object, meaning me, moved 10 meters from the reference point, the cat. The triangle or the delta symbol shows that the number is a change in quantity, so that's very important. Now, the thing about scalar quantity is that it gives no information on what direction I went. For all you know, I could have jumped 10 meters in the air away from the cat. This is where displacement and vector quantities fill in the gaps. So let's talk about displacement. Displacement is a vector quantity. It is a measurement of the change in distance from a reference point and the direction which the object is moving. So let's use the same example of my farting cat right here. To determine my displacement relative to the cat, you would need both my beginning position, so at the cat, and the final position, and the directions that I moved in. You can record the displacement, in this case, as delta d equals 10 meters. Bracket, right, because I moved to the right. This indicates that the object, meaning me, ends up 10 meters from the reference point, this little cat. It also indicates that the direction of travel was to the right of the reference point. So I moved to the right of this little furball. Let's make things a bit more complex now. All right? Okay, bye. Let's use the same scenario, but instead of me only walking 10 meters away from the cat to the right, I also turn around and walk 12 meters back past the cat. So I go 10 meters to the right and then turn around and walk 12 meters back. This makes the total distance I travel to 22 meters. So I travel 10 meters to the right and 12 meters to the left. In the previous example, the magnitude, meaning the amount or value of both the distance and the displacement, were the same. They were 10 meters. The total distance I moved was 10 meters, and I am also exactly 10 meters away from the reference point, meaning the cat. The difference between the two is that displacement has a direction indicated. The distance, delta d, is the total distance I traveled on both sides of the cat. So delta d would be 22 meters. Again, 10 meters to the right and then 12 meters to the left. The displacement is my change in position relative to the cat. So at the end, the little fur ball and me are only 2 meters apart because I'm only 2 meters to the left of the cat. The calculation would look like this. 10 minus 12 equals negative 2. In normal circumstances, we give any movement to the right a positive integer and any movement to the left as a negative integer. Here is another example for displacement. Let's say Mr. Drover is running a 400-meter race. The race is run on a 400-meter Olympic oval track. Since he ran perfectly in lane 1, I ran exactly 400 meters. What is my displacement? It's weird talking in the third person. The answer would be 0. Even though my total distance traveled was 400 meters, quarter of a mile, since I traveled to the exact point where I started the race, my displacement is 0. Wow, that's crazy. That's crazy! Note, it is an important part which should not be overlooked. When you are describing motion, and when you are recording distance traveled and displacement, you must indicate the change by using the delta symbol or the little triangle. This indicates that there has in fact been a change in the distance or the position of an object. So remember that, because that is a very important part of writing the formula out. In the farting cat example, the vector directions were given right and left. These vector directions were determined using the x-axis method, the horizontal line on a graph. Think back to math. Kitty, 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 kitty. You may also have seen vectors that refer to the compass directions, such as north, south, and east. For example, a plane flying from Calgary to Regina, which are Canadian cities, would have an E vector, which stands for east. This vector direction is determined using the navigator method. The x-axis method for determining vector directions uses the mathematical method of setting up coordinate systems with a grid, with an x-axis and a y-axis. Similar to a graph, directions are stated from the x-axis, which is the starting reference point at 0 degrees. From there, directions are determined in a counterclockwise direction, given along the x-axis and y-axis lines. They're given positive and negative values. The navigator method, on the other hand, uses the directions of north, N, south, S, east, E, and west, W, on a grid to identify vector directions. North, in this case, is the starting reference point of 0 degrees. In this method, directions are always stated clockwise from north. Directions are given along the axis lines have positive or negative values. In the case of the navigator method, north and east are always positive, south and west are negative, and directions between the axis lines are given not only the letter, but also the degrees, and they are not given a positive or negative value at all. So, if something is not exactly north, south, east, or west, we give the directions using degrees. Now let's look at speed and velocity a little more closely. Now that you know the difference between a scalar and a vector quantity, let's look more closely at speed and velocity. In our last lesson, you learned distance traveled in calculating average speed. Both distance traveled and speed are scalar quantities. Again, meaning only the magnitude of each one is stated. For example, the average speed of a car may be stated as 100 kilometers an hour. To calculate the average velocity, you use displacement. Both displacement and velocity are vector quantities, so you must state both the magnitude and the direction for them. For example, the average velocity of a car on the highway from Edmonton to Red Deer might be 100 kilometers an hour south. Using graphs to analyze average velocity. In our last lesson, you learned that the graphs are an important tool for studying uniform motion. They show the relationship between two variables and provide a visual representation of the motion. You saw how distance time graphs and speed time graphs are visual representations of the speed of an object. You also learned to use graphs to calculate the speed and distance traveled by objects. To analyze average velocity, you can use two types of graphs, a position time graph and a velocity time graph. When you were plotting a position time graph, last lesson you considered speed and distance traveled when I was driving to the gym. Now consider its velocity. Suppose I wasn't on a cruise control and during the drive, the gym I passed by 10 intersections placed 1,000 meters apart. A person near the roof was recording it every time I passed by an intersection. The table on the left shows those measurements. The graph on the right uses the data from the table to describe the motion of the car visually. The line of best fit indicates a linear or a straight line relationship between the position and the time taken to travel. This means that as time increases, the position also increases. The straight line of a graph shows that the car's displacement in relation to the time intervals is constant. Therefore, me and my car are moving with uniform motion. My velocity remains constant. You can use the slope of the line in our graph to determine the average velocity of the car. A velocity time graph is similar to the speed time graph we looked at last lesson in driving to the gym example. People studying the car's motion would keep track of both the speed and direction to determine the velocity. Suppose the car is traveling east at a uniform velocity, past 10 intersections 1,000 meters apart. The person calculating it has a stopwatch, and he has a compass to determine the direction. Let's look at the measurements they took. Here is the graph of the data from the previous table. The line of best fit is a straight line. This indicates a linear relationship between the velocity of the car and the time it took to travel past the markers. The line is also horizontal. This means that the velocity remained constant during the time the car was moving past the intersections. The car is traveling with uniform motion. Next, you'll learn about motion that is not uniform, when objects increase and decrease velocity. What? On a long-distance flight, your plane may fly for long periods at 900 kilometers an hour, unless you have a window seat. However, it may seem like that plane is not moving at all. Uniform motion can be relaxing. Even at such a high speed, the excitement comes at the beginning of the trip as the plane takes off. The speed changes rapidly from rest to takeoff speed in several seconds. Because the airplane's speed is increasing, so is its velocity. This change in velocity during a specific time interval is called acceleration. You can experience acceleration in a vehicle or on your own. For example, when you start to run for the bus or dive into a swimming pool or start a 100-meter race, you are accelerating. Let's look at the type of accelerations now. Uniform motion is the simplest type of motion, but accelerated motion is the most common type of motion. Like velocity, acceleration is a vector quantity, so you must determine both the magnitude and the direction. Different types of acceleration are possible because both the magnitude and the direction of velocity can change. When an object is speeding up, the magnitude of its velocity is increasing. When an object is slowing down, the magnitude of the velocity is decreasing. Positive acceleration occurs in two ways. One, when the changes both magnitude of the velocity and the direction are positive, and two, when the change in both the magnitude and the velocity and the direction are both negative. Wow, sorry, I glitched there. Negative acceleration also occurs in two ways. One, when the change in the magnitude of the velocity is negative while the direction is positive. Or two, when the change in the magnitude of the velocity is positive and the direction is negative. Using formulas and graphs to analyze accelerated motion, you can study accelerated motion quantitatively by using formulas and graphs. To calculate the acceleration, use the following formula. Acceleration equals change in velocity over time intervals, where change in velocity equals final velocity minus your initial velocity. And VF is the final velocity and VI is the starting velocity. Just make sure to draw those arrows. Remember, acceleration is a vector quantity, so you must determine the magnitude and the direction of the acceleration. Right, kitty? Acceleration. Plotting a position time graph. Alright, so earlier in the video, you learned that you could determine the velocity of an object from the slope of a position time graph. The line of best fit for an object traveling with uniform motion was shown to be a straight line because the velocity was uniform. For accelerated motion, on the other hand, the line of best fit is a smooth curve. Here's an example. Suppose that a motorboat is traveling with accelerated motion in the east direction. It passes markers placed 5 meters apart. As the boat passes the first marker, a person on shore starts to estimate and record the position of the motorboat for every 2 seconds, relative to the first marker. This table on the left shows the data collected by the person on the shore. The graph to the right describes the accelerated motion of the motorboat. The slope of the line is gradually increasing, which indicates that the velocity of the boat is gradually increasing or accelerating. The shape of the curve of a graph of accelerated motion indicates whether the object has a positive or negative acceleration. These next two graphs are position time graphs of accelerated motion. The graph to the left has an increasing slope, which indicates positive acceleration. The graph to the right has a decreasing slope, which, you guessed it, indicates a negative acceleration. Let's look at plotting a velocity time graph. Again, suppose that the motorboat is accelerating in the east direction, and a person on the shore uses a radar gun to record the velocity of the motorboat, like a police officer does on a highway. The motorboat passes a marker every 1.0 seconds according to this radar gun. The graph to the right uses the data from the table on the left to describe the accelerated motion of the motorboat. The graph shows the line of best fit for this data. This is a straight line with an increasing slope. This indicates that the velocity of the motorboat is increasing with time. The slope of the line of best fit can be calculated as follows. Slope equals rise over run, which actually equals acceleration. And remember, acceleration, the formula is change in velocity over timed intervals. Plotting in the data from the table, we get this. 10.0 meters per second east minus 0.0 meters per second east over 5.0 seconds minus 0.0 seconds equals 10 meters per second over 5.0 seconds. That equals 2.0 meters squared. The acceleration of the boat is 2.0 meters squared east. If the slope had a negative value, this would indicate that the boat has a negative acceleration. In other words, it was slowing down. So that's it for this video, folks. I know it was a long one and there's a lot of new terms thrown your way. However, by pausing, rewatching, and carefully looking at the video, also by taking notes, I'm sure with practice this will all seem easy sooner or later. But before you go, please remember to hit that like button and subscribe to the channel. Just in case you miss a video, this will ensure that you never do. If you are still hungry for science, you can click on any of these videos to continue your scientific adventure. I'm Mr.Drover, and this is Oi the Bengal. I hope you had a fun day and learned something. I will see you next week.